For decades, testing prototypes for airplane wings, car components, heart pumps, or HVAC systems such as this required the building and parts be measured about how the fluids flowed around them. Brian changed all that, saving time and expense while improving safety. He has spent his career developing new methods of mapping fluid movement to create the accurate models that engineering and science require. His work has affected countless of engineers and researchers, including myself. In my PhD thesis written in 1980, I cited Spalding's publication, A Novel Finite Difference Formulation for Differential Expressions Involving First and Second Derivatives, published in the International Journal for Numerical Methods in Engineering in 1972. Born in England, he attended Oxford for his BA and MA, graduating in 1948. He earned his PhD and SCD from Cambridge in 1952 and 1966, respectively. He has taught at the Imperial College of Science, Technology, and Medicine since 1954, where he is now Professor Emeritus. In 1974, he founded Concentration Heat and Momentum Limited, a world-leading consultant company with offices in more than 25 countries. CHAM helps its clients with computer simulations of fluid flow using Spalding's pioneering software that Dr. Runchel just referred to. His method for modeling is known today as the finite volume method, and the code, of course, we all know now as Phoenix. It's used by environmentalists monitoring air quality, architects monitoring building air movement, and car designers seeking performance and efficiency, to name a few. Dr. Spalding's award include the Institution of Mechanical Engineers James Clayton Prize, the American Society of Mechanical Engineers and American Institute of Chemical Engineers Max Jacob Memorial Award, the Institut French glasses, Institut Français de l'Énergie Médaille d'Or, the Combustion Institute Bernard Lewis Medal, and the International Center for Heat and Mass Transfer's Lukoff Medal, and finally the Global Energy International Prize. Dr. Spalding's talk is most appropriately entitled Benjamin Franklin and CFD. Ladies and gentlemen, I present the winner of the 2010 Franklin Medal in Mechanical Engineering, Dr. D. Brian Spalding.
Thank you, Jerry.
Yes.
Thank you, Jerry. Ladies and gentlemen, it's a great honor to be here, but honors have a way of being a bit daunting, and I must say I feel very more daunted than honored at this moment. It's a great pleasure to be talking with you, to see among you various, can I say, old students? Not old, of course, but I wish they would stand up just to know, so that Malcolm, Steve, Andrew, where are you? Please stand up just to show that there was continuing CFD development at Imperial College after actually I left. Fine, thank you very much. Well, I'm daunted also because I sent an advance copy of this lecture, which I'm about to give, to Suhas Patanko, whose picture you saw, asking for his opinion, and asking particularly whether the ideas I'm putting forward here would be understood. And his answer was, frankly, no. And so I was fortunately marooned in Moscow by this volcanic ash, and I had 4 days to try to patch up some of the defects to which Suhas drew my attention. I don't know whether I've done it, but we'll see. So now, with the talk, Benjamin Franklin, CFD. First thing is to get the title for a lecture, and that came very quickly. It was much harder to decide what to put afterwards. But at any rate, I have strung some things together with some ideas which I do genuinely want to transmit to you, and I hope that I shall succeed. So let's go. Yes, fluids played a very large part in Benjamin Franklin's life. He wanted to be a sailor, but his father, tallow chandler, so melting tallow and making candles was what he had to do. Then there was his printer brother, to whom he was apprenticed, not very happily, and printer's ink did become his career fluid. But he was always interested in water. He was a good swimmer. He became a swimming teacher in London one time when he was here. But when he absconded to Philadelphia, he went by water, and he spent quite a lot of time immersed in it because they had some problems. And it was raining when he arrived too, as I too have experienced. Later on, his fluid, the fluid of interest was gases. He made his inventions of lamps and stoves, and I am, in this lecture, just speculating about how he might be exploiting CFD were he alive today. In 1774, he sailed for England in a ship which the captain thought was pretty good. I think he boasted about it, but when they got to sea, they found that they were being left behind by the others in the convoy. And so the captain, being an ingenious man, got the passengers on deck and the crew and moved them around and finally huddled them in the stern, and he found that then the ship mended its pace, and he concluded that the cargo had been badly distributed, about which Franklin remarks on the lack of coordination at that time between the hull designers, those who loaded the ship, those who trimmed the sails, and so on. And he said that a set of experiments could be instituted to determine the proper form of the hull, proper place for the mast, etc. He was always thinking ahead, and he was sure that some ingenious philosopher, as he called him, would undertake it, to whom he wished success. Well, I feel sure that if CFD had existed then, he himself would have become that philosopher. Now, CFD has made some contribution to sailing vessels. I know those are not as prevalent as they were, but Gordon Mallinson, a former colleague of mine, can claim some credit for the success which New Zealand had in the yacht races of the late 1990s. So he had a virtual wind tunnel and a physical wind tunnel, and he, in that way, calculated the flow around the sails. Now, that's not very difficult, you might say nowadays. So I thought I would try to just draw attention to a different fluid mechanical phenomenon, which I didn't know about, but which has some CFD connections. It's the so-called dead water effect, which is a sudden slowing down of your ship, as though an anchor has been dropped. And around the surface has a glassy look, and there's a prolonged hissing sound, it is said, over a wide area, and the ship becomes hard to steer. Glassy surface, turbid edge, that's how it's been described. And one person who described it particularly was Nansen. And these are the striking words. They were moving at 5 knots when the speed suddenly dropped to 1 knot and stayed that way. And the moment the engine stopped, it seemed as if the ship was sucked back. That's his vessel, sails and engine it had. And the explanation, in that area, evidently, there was a subsurface density interface. There was a density stratification, and the ship was actually generating waves in that subsurface water. And this has been subjected to both experimental work and computational work. And you see on the right there, at the top, the model ship, and beneath it you can see the variation in color, and that has been simulated by CFD, by Bob Hornby on the left here. And agreement between the experiments and the prediction was very good, because despite that hissing sound, of which I don't quite understand the reason, there is no significant turbulence. So the agreement was satisfactory. And I think that that is one of the kinds of experiments which Benjamin Franklin would have liked in fluid dynamics, had he made any, because they had that excellent quality, simplicity, which he praised. But now I move on, and I'm glad that Frank Harlow mentioned combustion as an interest of his, because I believe that it has something to teach us. And Benjamin Franklin was strongly interested in combustion. First of all, he corresponded with Joseph Priestley, who was our discoverer of oxygen, and But these were days when oxygen was not really a common word, and when he saw the experiments which Lavoisier was making, burning charcoal, he called it experiments with dephlogisticated air. This was a time at which the phlogiston theory had not yet been fully debunked. And then on the practical side, Franklin invented his oil-burning lamp, having observed that the oil lamps, which were spherical, which they got from London, easily became sooted, and he concluded that it was because there was insufficient air entering, and the smoke which had formed would blacken the glass. And his plain glass sides with the cracks at the corners allowed the air to enter. And also he was concerned with flow of heat and air from furnaces. I understand now why he was concerned with heating here in Philadelphia. and he concluded that it would be better to bring the fire from the fireplace into the center of the room, in the stove, so that it could then heat the room properly. And I similarly, I'm following him in bringing combustion into the center of the CFD stage, because I believe that it can tell us something about CFD generally, and particularly turbulence. So that is how I should proceed in this lecture. And I say there were two reasons why CFD specialists should be concerned with chemically reacting flows. First of all, if we didn't have the engines, we wouldn't have the aircraft flying. And if we didn't have the, and there wouldn't be in the reactors the flows which we need to simulate. And the second reason is that studying combustion can provide a unique insight into turbulence, an insight which is relevant in fluids without combustion. And so I say, what would Benjamin Franklin notice if he were looking at turbulent flames today? Well, their intermittency, just as Frank Harlow pointed to the intermittency of the turbulence of the St. Helens volcano eruption. The intermittency. At one location, there may be, at this moment, air, next moment, fuel, and in the intermediate periods, partially burned fuel-air mixture. So intermittency. And I thought that he might, thinking about this, as indeed to a certain extent Frank Harlow did, think about the population of gases there. We saw Frank Harlow had his population, and that I thought is how Benjamin Franklin would think about the combustion process if he were to return, because he was aware how colonists and Indians would be continually interchanging in those turbulent times of early Philadelphia. And then it goes on, and I hope it stops soon. Yes, it stopped with a certain amount of peaceful interaction between these two. But so thoughts of that kind might be in his mind when he thought about combustion. Because he was a methodical man, and he particularly liked representing ideas graphically. This is the chart on which he charted his, I can say, moral progress. Every blob there was a departure from one of the standards which he had set himself: T for temperance, S for silence, O for order, and so on. I can read at the top, can you? It says, "Eat not to dullness, drink not to elevation." And he had other good words for himself too. But he expressed his ideas graphically. And what would he do about combustion? I thought he would very well invent a two-dimensional diagram to represent the population of gas states between fuel and air and so on, which you found in a flame. And I thought he might have invented that diagram, in which you have the two things which enter, the fuel and the air, and then what comes out at the end, the fully burnt gas. But anywhere within the flame, there is a population which we represented by a distribution over that triangular diagram. And think about that diagram, because I'm going to use it quite a lot. It represents the possible gas states. Every state in the flame will be at one point, at one moment on the flame. I said he might have called that the trimix diagram because it's temperature rise, which is the ordinate, and the mixture ratio, fuel-air ratio, between fuel and air, which is the abscissa, and product hot at the top, and the air and fuel cold at the bottom. Yes, here the words I've just used, temperature rise, mixture fraction, and here is what might represent a population. Quite a lot of gas in the area represented by the red colors, and the contours show how it is distributed. So such a diagram can represent the population of gases at a particular point, representing how they interact, come and go. And yes, it will be used, and I'll do it now, to show how the properties of the gas can be represented, and I shall also be later using it to illustrate some of the hypotheses which have been used. So I'll call him RBF, returned or maybe reincarnated Benjamin Franklin. He will want to represent the composition of the gas population on his diagram. Here they are. Here's on the left the amount of unburned fuel. It's big on the right, small on the left, and free oxygen. The temperature is high at the top, the adiabatic combustion temperature. There's a bunch called the reactant, the extent of reaction which is taking place. And finally, combustion of concentration products, they're highest up at the top. But there are other properties also which can be represented in this way. And I'm going to suggest that Benjamin Franklin would use this to enlarge his understanding of what happens in flames. Now, after Priestley and Lavoisier, there came this guy Arrhenius, who explained how it was that chemical reactions were much faster at the higher temperatures, and the results of his findings could be represented. I see here there are three kinds of reaction which one's interested in combustion chambers. There's the main reaction, the one we want, which will turn the fuel and the oxygen into combustion products and produce heat. But then there are undesired reactions which produce oxides of nitrogen and which produce smoke. On that diagram, it's on your left, it is there's more air, on the right there's more fuel, so we find that the main reaction is strong in the middle, the NOx reaction on the side where there's more oxygen and nitrogen, and the smoke on the fuel-rich side. I say the smoke is undesired, but not entirely, because Franklin wished to give light from his lamps, and that it is the radiation from the smoke particles which provide that light. Well, this is what I thought, that once he'd got into his mind what flames were like, how the gas varied from place to place, then he would immediately begin to see what he needed to do in order to design a reactor. And I think, being a sailor still at heart, he would visualize the process of his good ships, primary air down here and fuel here, meeting at about the right mixture ratio, sailing up north to through the region of high reaction here until they became completely reacted. And then, because maybe it's for a gas turbine combustion, you can't put the very hot gases through the turbine, you've got to add in secondary air, you've got to add in air, more air from the bottom down here, secondary air it's called, and they'll meet together, and then gas of modest temperature goes out. Yes, so in this process you've got to avoid what I call the Scylla NOx on the left. You don't want to get into that region, you don't want to get in that region where there's too much smoke, you want to go through the main reaction region and then get out fast. And so that's how they go out finally. And so his ideal design for a combustion chamber might have looked like this, three parts. First of all, mix the fuel and air in the stoichiometric region. Yes, I've got that here, so as to go up to the fully combusted state, fully combusted here. Oh no, yes, sorry, they get here to the most intense reaction region, then that's got a burnout. You go down to the top here. It's burnt out, now it's fully burnt, and at this point you introduce the secondary air in order to cool it rapidly, in order to get the gases at the right temperature, and you must do that very fast because you don't want to go through the NOx region. And if he were then, having come back and just invented the gas turbine combustor, impart his ideas to an actual gas turbine combustor, he'd be told, well, that's really just what we do. Here's the combustor. We do put the fuel and the air into some region here where they burn in the upstream part, more or less in the stoichiometric mixture ratio. And then downstream we've got holes in the walls here, and the secondary air comes in and the gas goes out at its cooler temperature to the turbine. So he's told that's what we do. But then he's asked, all right, that's how you do qualitatively, but now how do you design it in the sense that you decide how much air to go through these holes? How do you determine the sizes and the positions of those holes, etc.? And his CFD specialist would say, we use CFD. About which, of course, our reincarnated Benjamin Franklin does not yet know anything. So he asks and is told, what we all know, that it's computer simulation. It applies conservation laws, conservation of mass, momentum, species, etc., to a grid of finite volumes. And then it solves by trial and error. Well, I thought that Benjamin would understand that completely, because he'd immediately understand all you need is the skills as a storekeeper. What comes in, what goes out, what's created, what's destroyed. Do that many, many times over all those cells. He'd understood that, and he would say, okay. And also, he had studied arithmetic. He had very poor schooling, but he did later on in his life, in his more mature age, in his 20s or so, he had studied Cocker's arithmetic, and he found that was easy. And besides, trial and error was a general method of solving problems for colonists in a new territory. I see, said Benjamin, and I suppose you do the same thing for the gas population distribution too, because he's got his diagram in his head, and he would immediately imagine that, of course, you divide that up into spaces too, and you've got a population grid, and each of these has a particular value. Each cell in it has a particular value of the fuel-air ratio and of the degree of reaction and so on. What's a gas population is what the specialist So, Benjamin explained this diagram. Thanks to provide the instruction, you're dealing with those. Don't you discretize those as well as space? I've heard of that. As a specialist, we just use ANSYS or some other code like everybody else does, and really doesn't want to look any farther. But then Benjamin persists, but look at these turbulent fluctuations. And at each different temperature, the reaction rate is different, and the NOx production is different, and so on. What do you do about those? And so the specialist said, right, I guess we just take the time average, the fuel air ratio as well. Benjamin, well, but if you did take them into account, and you calculated the proportion of time in which the local gas, the proportion of time in a particular state, wouldn't you be able to calculate better rate of combustion, NOx, and smoke? Well, I suppose so. The specialist say, but how did we do that? Well, when he was young, Benjamin Franklin was a follower of the Socratic method. He very much liked to entangle those with whom he was debating by asking questions, question after question, and gradually leading them things which they hadn't known beforehand. And I think that is what he would have done with that CFD specialist, and would have led the specialist to agree, yes, there's actually no essential difference between geometric space, X, Y, Z, and population space, fuel air ratio, temperature ratio. Both spaces, no essential difference. And the same techniques, discretization, can be used for one as for the other. And for each, you've got a balance equation, and you can use trial and error solution. What's the difference? And it could be recognized that sometimes the distribution in population space is much more important than the distribution in geometric space. You have what appears to be a fully mixed region, but really it isn't fully mixed, although there's the same conditions, the same here and here. Few geometric variations, there are strong variations in population space. Some fuel, some air, some mixture, and so on. And so, by Socratic questioning, gradually the specialist would have to agree, yes. And if that's the case, that sometimes the population space is much more important than the geometric, isn't it absurd to boast that you have 1 million computational cells to represent your combustion chamber, the space, whereas you're using only one population element, just so it's always the things are fully mixed and unbalanced, it might be said. And then, just as in geometric space, we use grid refinement studies, finding out how fine a grid we need to get an accurate result, so we would do the same thing in population space. How many elements of the population we would need. And all those things which we do in computational dynamics, we can do in population space. And provided we don't, having got the idea, overcomplicate, then we can proceed. Well, this is the point at which Sue has said, okay, they won't go beyond this. So this is the point where I've had to put some more things. I'm saying that, okay, our CFD specialist has been browbeaten by the Socratic questioning. He admitted all those things, but do you admit them? Probably not yet. I think that you will probably need a little bit more time to accept those ideas and also some motivation. So in the remainder of this lecture, I'm trying to provide, I mean, some of you aren't interested in combustion at all, but you'll be interested, I suppose, in fluid mechanics and in velocity fluctuations. And so I would remark that if you're just interested in velocity fluctuations, then you could describe them by a one-dimensional population, proportion of time in a high velocity, low velocity rate, or what we call PDF for terminology. And then you would have a model which could explain how it is that when you've got a curved duct, the high velocity fragment get centrifuged out, the low velocity inwards. And so you can have a model of swirling flow, which you can't have properly without a population. I'm going to talk about it a little bit later. Similarly, gustiness is an important element in the wind flow. It affects human comfort, and it also has damaging effect when they blow turbulence down. So you need to know not just what is the time average, or even what is the root mean square fluctuation. You need to know the proportion of gusts, which are in really high velocity range. You need to know the population. So then there are, in other pure hydrodynamic areas, for example, let's take the dead water phenomenon. Sometimes you get two kinds of stratification, temperature stratification and density stratification. And what happens then? What kind of turbulence is generated? That should be described by a two-dimensional population. So I just want to say that, though I shall go back to combustion now, though I'm talking about it, the population idea has relevance to other phenomena of hydrodynamic interest. That's what I'm trying to convey to you, and I don't know if it'll succeed. First of all, it may appear that this is really a rather great enlargement. We've got a 3D grid already, and now I'm saying that for each place, there's a 2D grid of gas populations. And that is true. So for each point in the 3D space, you do have to, if you follow Benjamin Franklin's idea at least, you have to calculate how the fluid is distributed over the corresponding trimix diagram. The one cell here, there corresponds whatever number is in their cell. And you might say, we had a 3D grid, and now we've got 2D. We've got a 5D problem. That's a bit alarming. Yes, that's getting all those points. But it's not just alarming, but it's alarmist. It isn't that bad. All that has happened is that the 3D problem has acquired some additional variable equal to the number of elements in the 2D grid. It's not truly 5-dimensional. The 3D problem has acquired some additional dependent variable. And here's an example. Suppose without the population dimension, we have the common pressure, 3 velocity components, KE, epsilon, mass fraction, and so on, temperature. But we will add to this. We'll actually drop the F and T, so we'll have the first ones, P, UV, KE, epsilon, and as many equations as we decide we want cells in the population group, which might be anything between 10 and 100, but let's say 20 is typical. So it isn't an enormous, it isn't an immense computer time increase, and as I shall say, it's quite practical. Now, we've got to think about the physical processes. They're different in the geometry, in the population grid, but it is can be considered. What we say here, in the geometric grid, neighboring cells influence each other by means of diffusion and convection. Oh, and there's also the word, if it's a population, there's something called differential confusion. Not all the elements of the population need movement at the same velocity. But I'll come to that later. Now in the population grid, there is what I call an engulfment process, whereby different elements mixed together, they become engulfed, and so the movement along a diagonal towards the middle. But there's also something, that's on the left, something which is akin to convection, it's movement along grid line. Gases tend to move from the unreacted state to the reacted state, so they move in that direction. But these are phenomena which one can express in the form of equations, and so it is not totally different from what we do in geometry. Gives us a little bit more about the same. What is our task on this population grid? We need to find the value of concentration of material, how much material is in any of these cells. And we'll get a distribution. We're taking into account of these convection-like movements where we find material moves from one cell to another because chemical reaction is taking it there. And we have also the intermingling of remote elements. They come together, they get mixed up, and so they produce material of an intermediate composition and temperature. What is the rate of that last process? That is new. It can be related to the shear process in the basic flow. That was first done in what was called the Breakout Model, which actually I mentioned, but it had one empirical constant. And I've got a slide here which just shows what I mean by it, which is this engulfment process which you can see in theoretical calculations or in experiments. The process whereby it is roll-up, and it said here, two recognizably different fluids which are lined close together, they slide relatively to one another, and then this roll-up occurs, and the interface between them becomes stretched, the thickness of the interleaves becomes thinner, so molecular diffusion and heat conduction can take place,
And so the amount of that mixing per unit volume increases enormously. And that is essentially the process which I have to express by way of equations, and so can describe the movement in population space. Yes, there is that element, I call it differential convection just now, whereby different elements of the population move at different speeds. Villanians can run and ride faster than colonists, Benjamin Franklin would know, and they often attack what the latter flees from. And so there are different speeds, and that's just to illustrate that in combustion chambers, pressure gradients force lighter hot fluid to move relative to the cooler or denser fluid. That's differential convection, or I use the word filtering here to try to describe it. In this lecture room, hot air rises, it says here. I don't think there's very much hot air. Anyway, I'll skip that one. But then, going back to that flow on a curved wall, the faster moving fragments move outwards, the slow moving ones move inwards. That is differential convection or swirling. And all of these can devise mathematical expressions, but it isn't new. We're not in suddenly new ground. For example, in sedimentation processes, we've got particles of different size, different density, and some go down and some go up, and all that is in multi-phase flow. CFD, it's known. And we simply need to apply to our different populations of combustion the things which are familiar. Well, we don't talk about population in CFD, but maybe that idea is recognized in different words. And so this, I go back to the eddy breakout model, which, though we didn't use the word population, wasn't that kind. It imagined that the combusting gas consisted of just two elements, it's a two-element population, fully burned and fully unburned. And it was a hypothesis which enabled us to explain phenomena which until then were difficult to explain. Here is the flow, the flame behind the flame holder in a duct, and what Skerlock found, it was 1948 or so, which is very puzzling for those who knew about laminar flames, that you can increase the velocity, you can change the fuel aeration, and do everything, but that angle remained almost the same. And that was because it was controlled by the engulfing process. And formerly with a mechanical constant device, and that's been used ever since in one form or another. That if you want to represent the eddy breakup model on this trimix diagram, we take two red squares here and here. Those are the fully burned and fully unburned gases which mix together, and then the hypothesis is that once they mix together and produce some intermediate temperature fluid, that can react rapidly and it all shoots up to that. So that is the eddy breakup model. And it's still indirectly used. It underlies almost all combustor calculations. So we're not in new ground here. If we go to the Benjamin Franklin's group for the we will just be able to use things already available. I mentioned here other tentative steps into population space. There was a two-fluid model which showed how the model of transition to detonation, showing how colder elements, this must be time here, not the velocity in that direction, as the detonation developed, the colder elements moved, they were accelerated, but they were accelerated less rapidly than the hotter elements on the right. So that was a tentative step in the population dimension, and taking account of the different velocities of the elements of the population. And there were lots of others. Any dissipation concept can be represented here. It's similar to any breakup. It has two rather less well-defined points, and there's flamelet and so on. There are various hypotheses, fragmentary movements in the direction of population. But as I think I've written here, none of those have recognized, as Benjamin Franklin did immediately, all we need to do is to calculate the distribution through the whole of the trimix space. Well, I am getting towards the end, I think. More serious steps into population space. It can be said that Pope's PDF transport model is of this kind, but it's using the Monte Carlo method, and many people find it rather difficult to understand. And it has been used, but rarely because of the computational expense. Then there is a multi-fluid model, which can, again, represent such phenomena, but the results display methods are perhaps not sufficiently simple to have been accepted. Nevertheless, you can see that there's a triangular space of occupancy here which corresponds to the triangle of the diagram. This was born in 1995, and it first was moved towards a four-member population rather than a two-member population, and it was used for oil platform explosion, which, rather curiously, the flame spreading across even the oil platform is colored green. And maybe multi-fluid was a bad choice because it suggests something physical, whereas really fluid was just used for an element of the population space, no more real fluid than as much a figment of imagination as the CFD specialist divides geometric space into his cells. And now I'm just going to conclude by showing that MFM model has more general utility than for combustion by showing two non-combustion applications. Both, in fact, use only one-dimensional populations. First of all, a stirred chemical reactor. And a lot of the materials which we ultimately use have been created in stirred reactors, and then let's flow and occur by away. So here it's an old CFD benchmark problem, one in which one is concerned with two materials, let's say acid and alkali, to make it simple, which are being stirred in a reactor. It's a CFD calculation of that kind, but mostly they don't even think about the population. They just think we'll stir it all up and take the time average. But what is going to be shown is that if you do that, you neglect the population effect, you get answers which are considerably different from those taken into account. So in our case, we've got these two cases, and for the multi-fluid model, we have only 11 equal parts in that space. I'll go over here. So I'll show you a contour diagram, three-dimensional contour diagram of not the population, but what results from it, the product, the diagram of the concentration of contours of the product. And for cases 1 and 2, one without population effect, 1 and 2, you get different results. That's the important thing. And you also get quantitatively different results about the total amount of product. Large but significant. And if you're designing a chemical reactor, you need to take account of the fact that to neglect the lack of complete micro-mixing is to get a wrong answer, to overestimate the performance. And the explanation is that for each position you have calculated one of these one-dimensional, now PDFs, representing the distribution in the various little pockets. Each one is reacting at a different rate, and that is why, whereas to neglect population making, you've got just one column at one place. If you take account of the full distribution, then you get more accurate results. And now this is the last example, which is my, I just picked that up from a lecture given on swirling flows to illustrate that filtering process. We're thinking of the flow between two rotating cylinders, and we used an existing 17 fluid model of Zubrin and Kravitsky. We chose the rates of ratio of turbulent engulfment to diffusion, which fits experimental data of channel flow. Introduce now a hypothesis for the relative motion of the thrust of the centrifugally flung out and the centrifugally pushed in fluids. And so that is formulated mathematically, and I will just show you the last results. Here we see, this is now the duct, the distance along here. These are the concentration of the fluid. This is the concentration of high velocity fluid. First of all, this is with no swirl. The medium velocity fluid is along the middle here. The low velocity fluid on the in the inner wall. Nothing surprising about that, except that we are getting the distributions of the population represented by contour diagrams. And now, effective filtering. These FPT, fluid population distribution. Oh, I can't even get the letters consistently here. Here, I'll show you all three diagrams at once. In the first, this is with no centrifugal flow, it's a straight line. Here is a situation where the average velocity increases with radius and the PDF becomes, so the central plane becomes steeper, and now reverse the population, the PDF becomes fatter. What has happened is that because of this relative motion of differential convection, the population distribution has changed, and so it is the shear stress. But now I'm at the end. For some of you, this notion of population really is perhaps novel, and I can imagine three reasons why you are against it already. First, it arose out of combustion, which doesn't interest you. Secondly, it seems to have rather enormous ramifications. You must surely require large computer resources to use it. And also, to this familiar menagerie, I call it, of convection, diffusion, and time dependence, we've added two new animals, engulfment and filtering, which may not mix with the others at all. So I've attempted to argue that in these, the non-combustion phenomena also involve flow of air, swirl, gusts, and so on. These elude conventional methods. Conventional turbulence models simply do not describe these processes of relative motion, so that we need, therefore, population type analysis. I've indicated that no vast resources, or ordinary people with laptop computers have done these calculations. No vast resources are needed. And I've argued also that these engulfment and filtering concepts have been already in use in different places for decades. We simply have to use it. However, what I'm not claiming is that anything more than pioneer settlements have been planted in this new territory. What we want is hordes of industrious new immigrants to populate it and exploit its resources. Well, I've tried to convince you, I hope I have, that what Benjamin Franklin returned immediately saw the analogy between geometric and population distribution is the correct one. That apprehensions regarding its unlimited extent and difficult implementation are not well founded. And so the question I pose is, why are we not doing it? Why do we not, as a matter of course, solve in the population space as well as in the geometric space? Not just for combustion, but for purely hydrodynamic phenomena which need it. We can choose arbitrarily how we break up this population space. It will depend upon a particular concern. If we're concerned with flying through volcanic ash clouds, then we'll be very interested in the particle size distribution and how that is influenced by the relative drift of the particles. And I say that there's a great future in front of it, because although the multi-fluid model example which I showed rode on the back of the K-epsilon model, you could have a standalone multi-fluid model which did not require KSI whatsoever. But the general conclusion I would like to leave with you is that we have as much intellectual territory to explore and conquer as Franklin's contemporaries, perceptively. That he found that he met with objections and reluctances, as he called them, and he soon realized that the best thing to do was not to represent these ideas as his own at all, but to put himself as far as possible out of sight and say that this is a scheme that some of his friends had suggested. And in that way, it went along very smoothly, and I can heartily recommend it, he said. And so I'm going to follow his advice. So I represented this population analogy as his idea. and so that's how I'd like you to keep it in your memory. So if you talk about other people, oh yes, Benjamin Franklin said something about that, you would say. And so you can be my friend, and then this idea may very small. And for that kind of service, thank you for your attention.